Got it. All right. Now, first thing first. This is what my timetable look like. So we are here. And there is supposed to be another session tonight at 7 p.m. I don't know who do that, but that's what I see here. I look at the class list, and I didn't even know that we have so much students in electrical engineering. Because combined, it looks like about 70 people. So I guess we'll have to do the 2 sessions. I don't like it, but I don't see I have a way out. Because half of 70 is 30, and to get everybody to come to the first lecture, it would be like a bit of a stretch. So let's see how the first couple of weeks work out. Now on Thursdays, we have labs. Obviously tomorrow we won't have a lab session because there's nothing to lab about yet. So I guess we'll start labs next week. So don't worry about labs for tomorrow. Again, we have 2 lab sessions. So I guess one is for this group and the other for that group. Yeah, so again, we'll see how that turns out. So don't worry about tomorrow. You have a free day tomorrow. You don't have to worry about the labs. So that is,
Sir,
yes.
how will the labs be conducted, sir?
I can't answer that right now. I know that it's more than likely gonna be it's gonna be virtual. Right? I have to look further into the assigned labs and see if there are any that we must go in the physical laboratory to do. And I'll inform you accordingly, but I can't answer that 100% right now. Okay?
All right, sir.
All right. So that is that for timetabling. Now, let's look at the syllabus. Normally, the person who teaches this class is Dr. Thorpe, Dr. Balvin Thorpe. But he's off this semester, so I have to step in. It's a 4-credit course. You should have done Math 3, differential equation and application as prerequisites for this course. So the module objectives: to understand the principle of communication theory, appreciate the different type of modulation techniques, and how to analyze and design a communication system. Now, I take it that you guys have been given the syllabus already, right?
No, sir.
No, sir, we haven't received any material pertaining to this course.
Okay. What I want you to do for me, see, you have a WhatsApp group, right?
We have one.
Every course I know have a WhatsApp
Yes,
group.
sir, there's a WhatsApp group.
Okay. I would like anyone, take responsibility to send me their email address, and I'm going to email you this syllabus, and you post it up on the WhatsApp group for me. Also, I'm going to ask that you add me to the WhatsApp group.
So, sir,
Mm-hmm.
you're not going to use Moodle no at all then, right, sir?
So, you like Moodle?
Sir, just feel like post the things me there talk, sir.
I can post it on that, but let me post it in the WhatsApp group also. So you can go through the details of the syllabus. Obviously, we have to adjust as we go on according to how fast you grasp the specific concept. All right. Now, this is the favorite part. This is what most people are interested in. Or will they be assessed? Okay. This is what I have here from Mr. Top. Test 20%, assignment 30%, lab 10%, and final exam 40%. So this test would be your midterm and then your final. So you have a chunk here for assessment and lab. For assignment and lab. So if you do your assignment and your lab, it look like you almost passed. However, I was told this morning by Mr. Dunkley that there was a revision to the communications syllabus. Again, she sent me this. I don't know if this is the revised version or the original version. So while we are working with this, I might inform you next week or so that we have to change the breakdown. My request is that your midterm and your final be face-to-face. I hope no one have a problem with that. These are your texts. You might want to add to that the series in communication systems. So again, the syllabus writer is Mr. Top.
So, sir,
Mm.
the field trip, I'm gonna be a virtual field trip, sir.
Where is the field trip? I'm not saying no field trip.
Sir, you know, see, you know, the hours there, so, sir. Breakdown of hours, sir.
Right here. Oh, you're gonna have virtual field trip, brother. You can have virtual field trip. Might have to replace that with a guest lecture or something like that. Because this COVID figure, which I think I have as we speak, is running rampant. Any other question on the syllabus?
No, sir.
Everything. All right. Let me look again. Again, we only have 16 people. All right. Now, this is version of Zoom that we are using is the introductory version where we have to restart every 45 minutes. So don't let that be a problem, please. All right. Now, For an overview of the course, I have copied from the University of Florida. So I'm going to ask you to follow this YouTube presentation. Okay? So that will be your introductory lecture.
I'm going to start today with some introductory remarks. First, we're going to review the outline of the communication system, and then I'll talk about, in particular, more about communication channel, and not so much about the physics of it, but the mathematical models that we're going to use for the class to model communication channel. So here's a block diagram of communication system. Let me draw it and then we'll discuss various components. So usually you would have some sort of information source. This is the entity that generates information. A good example would be me talking here. And then you have the next block, which is transmitter. Then we have something that we call communication channel. We have what we call receiver here. And then we have information sink. Okay, so that's a block diagram of a general communication system. The purpose of the communication system is to take the information from the source and deliver it to the sink. Now that's easily said, but that's actually quite a complex statement because of the how much difficulty we have in defining what the information really is. Even let's say transmitting something to the other side may carry less of the information if the other side already knows, right? I already heard it, so there's very little information, even though we went through the whole trouble of transmitting. So in this course, this notion of information, and although very important, is not going to be addressed in this course. We're going to actually narrow down what we consider a communication system and kind of look at only this piece here. We're not going to be concerned about information per se. We're actually going to look at these three blocks here and assume following, that we are not translating information from this side to this side, but instead we're concerned of sending signals from one side to the other. There's a difference because a signal may carry or may not carry information, but whether it does carry information is outside of the scope of this course. We're going to have some signals coming in here, and we would like to reproduce these signals as they come in the output. So what is, so I'm going to say here, there's a signal at this point, and there's a signal at the output. Now, how are these signals generated? Well, signals are essentially in our world voltages and currents. The information itself, or what we're trying to send to the other end, does not come as a voltage and a current. When I speak, it's an acoustic wave. When we're being filmed, that's a moving image that needs to be somehow captured and translated into a signal. So, big part of I guess information processing here is what we call transducers. So there's an input transducer that is responsible for translating signals. What are some typical examples of the input transducer? Your microphone, right? Microphone takes the acoustic wave and makes it a voltage. Your camera takes this image here and translates that into a whole bunch of currents and voltages. Your keyboard, it takes, you know, your these words and what you're trying to type and translates that into voltages and currents that are further processed by the computer. So our output in our system is input into our system is the output of the transducer. It's already voltage and current. The next block in this diagram is the transmitter. The purpose of the transmitter is to accept this signal from the transducer and adjust it so that it can be sent over the communication channel. The signals that are coming out of the transducers are typically what we call baseband signals. They're voltages and the currents at the low end of spectrum. When I speak, do you know what are the frequencies that are in my speech signal? If I were to look at this signal here, what is it made of? Do you know what's the bandwidth? So we're going to learn it, but it's up to 4 kilohertz in a telephone voice. You can, and if let's say I want to send that to a cell phone to a tower, can I transmit at 4 kilohertz? No, because it's such a low frequency. The antenna that I have, that I would have to have, would be like several kilometers big. So there is a block diagram here, or part of the communication system that will accept these baseband signals, do processing with them, and then adjust them so that they can be sent over the channel. If the channel is optical fiber, then it needs to translate this into the light. So I guess it adjusts the properties of the signal so that it can be sent over the channel. Now, this adjusted properties is a loaded term here because it does a whole bunch of things. I mean, this is a digital communication system. Transmitter will digitize your signal, perform the error control coding. It will modulate the carrier, upconvert, unconvert, amplify, do a whole bunch of things to adjust the properties of what is being sent here, so that it can actually go through the channel itself. So I guess depending on the signal and type of the communication system, transmitter may sample, quantize, encode, filter, amplify, and so on, right? We'll look some of these tasks when we start talking about modulation. So these are this first 2 blocks. Let's take a look at channel. What is a channel? Channel is a physical medium that is used for transmission of signals between transmitter and the receiver. So it's for signal transmission. Now, there are several types of channels, so let's kind of go through a list and try to survey them a little bit. So if I say communication channels, there are 2 major types. There is what we can refer to as wireline, and there's what can be referred to as wireless. There are wireline channels and then wireless channels. If you're talking about the wireline channels, you can have electrical and then line channel or optical wireline channel. What are typical examples of electrical wireline channel? There's something called twisted pair. Do you know what twisted pair is? Is that those two cables, the blue and white one that are everyone on the telephone landline. So, for example, twisted pair, coaxial cable, waveguide, and so on. Right? As our optical wireline channel, these are your optical fibers. And those are, the main channels that are kind of running most of our large-scale communication networks. Entire internet, landline telephony, voice and data all runs over the top of the optical fiber communication channel. Now, wireless, we have three types. We have RF channel. These are your EM waves of the RF portion of spectrum, which is, let's say, 3 kilohertz, 300 gigahertz. That's where the RF spectrum will reside. Then you have optical wireless channel. These are your communications in infrared. What would be a device that would use this kind of channel? Very popular device. Laser, okay, laser. Another one even more popular. Remote control. Don't forget remote control. And then there is another one which is acoustic, right? Now, both of these, RF channel and optical, they're both using electromagnetic waves, right? Just different frequencies. This is a lower frequency band, and this is a higher frequency. Acoustic wireless channel is different. It uses acoustic waves. What is the example of acoustic wireless channel? Underwater is a prime example because of underwater propagation of electromagnetic waves is just limited to few wavelengths, so you have to use acoustic wave. Even more obvious one is this one. When I'm talking to you, we're talking wirelessly, and we're talking to acoustic communication channel. Right? So these are all different channels, and just a high level, division between them. You can actually look at each one of them individually and kind of find out a whole bunch of examples. And they're all going to have different physical properties. On the outside, it seems pretty daunting just to deal with a wireless channel. And indeed, we have some courses, for example, wireless propagation that deals only with wireless communication channel because of its complexity, right? But from the standpoint of this course, we're not going to go into that great detail. What we're going to do is we're going to derive mathematical abstraction for all of these channels. We'll see how we can model them mathematically, and then later when you try to use all of this theory, you're going to say, okay, this is, for example, electrical twisted pair channel. This fits into this mathematical model. These are the parameters of the model, and we know how it will impact the communication system. Now, one of the biggest or one of the most significant properties of the channel is that it distorts the signal. In other words, what you place into the communication channel and what comes out of the channel are not going to be the same thing. That's universally true for all of these channels. They're going to change your signal. There are typically two ways how the channel can change. The change in the signal we're going to refer to as distortion. So the channel distort the signal. There are two ways how the signal can be distorted as it propagates through channel. So let me put that here as a note. The channel distorts the signal. And there are two ways, two types of distortion. time we're gonna call additive distortion. And the second type we're gonna call that non-additive, right? When we talk about the channel models, we're actually going to address these in more detail and see for a given model what types of distortions it will introduce, so that hopefully I'm just going to leave this right now undefined, and then when we go through the channels, we're going to talk in more detail what type of distortion does each one of them introduce into the signal. Now, the last two blocks is this receiver here, and of course there will be another transducer here. So let's talk about the tasks of these two. So RX stands for receiver. The purpose of the receiver is to accept this signal here. Now that is a distorted version of the original signal, and then try to recover what has actually been sent, right? So it's a very complicated task, even on the outset. You can see that channel may be more or less complicated. It can distort the signal in many different ways. And the receiver is the one who needs to cope up with it. It needs to actually look what it has received and try to recover what it has sent. So it does need to do. Actually, there's some of the part of the transmitter design are actually guided by what the receiver needs to do. So the transmitter does a lot of processing so that the receiver has an easier task at the other end of the communication. So I guess purpose is receiver accepts the distorted signal and tries and performs, I should say, its recovery. And as I said, there's a lot of tasks that it needs to do. We'll talk about some of these tasks, but in essence, whatever transmitter does to the signal, the receiver needs to undo. Whatever the channel does to the signal, receiver needs to undo, so that whatever came into this system, hopefully something very similar comes in the output of the system. And the last here portion is just the same comment as I had earlier. You know, the information that is generated in what is called native form is usually not the voltage or current. When I speak, it's an acoustic wave. So I cannot take this acoustic wave, translate it into voltage, and then just present the voltage at the output. We need to convert this voltage back to the acoustic wave. And there is a block here that is usually in the communication system for that purpose. In the case of acoustic wave, you have a microphone here that does conversion from acoustic wave to signal. You're going to have a speaker here that is going to take a signal and make it an acoustic waveform. You have a camera on one end, you're going to have some sort of screen on the other end, and so on. So there is always an output transducer. Converts signal into the native form.
Excuse me, sir, the video is silent. I'm not sure if it's my computer or it's on your end.
Hello?
The channel is still linear, therefore the convolution still holds. Right? So I
Guys, hello.
Hello, sir.
We'll wait until we 80% of the video to tell me you're not hearing.
Sir, a long time we are trying to reach out to you, here.
Yes, sir, we're trying to tell us, sir, but it wasn't going.
Is about 15 or 16 minutes since can carry back about 27 or something. Yeah.
Where is the something there? Settings?
In that red line, sir. It is
Yeah, but
Sir, I
yeah.
think it's because you had muted yourself. The audio stopped coming across.
Good Lord, man, then. So you say about here?
yeah, about there. If you would press play, sir, can tell.
No, we are here, sir.
You're hearing the video now?
Yeah, man, sir. Yeah.
not the voltage for a current.
Mm.
When I speak, it's an acoustic wave. So I cannot take this acoustic wave, translate it into voltage, and then just present the voltage at the output. We need to convert this voltage back to the acoustic wave. And there is a block here that is usually in the communication system for that purpose. In the case of acoustic wave, you have a microphone here that does conversion from acoustic wave to signal. You're going to have a speaker here that is going to take the signal and make it an acoustic waveform. If you have a camera on one end, you're going to have some sort of screen on the other end, and so on. So there is always an output transducer. Converts signal into the native form. Any questions about any of this? Okay. So let's now spend some time on the channel and derive some of the mathematical models of the channel. And that's kind of all the time that we're going to dedicate to the channel. Channel, as I said, is a relatively complex subject of this whole picture. But in this class, once we go to the mathematical modeling, we're going to use the models throughout the rest of the class. And we're going to focus on what is done by this block and what is done by this block. So let's talk about mathematical models of communication. Mathematical models of communication. Okay. So there are several mathematical models. In this class, we're actually going to restrict our attention to three. Right? So we're going to consider three mathematical models. We're going to give them following names: an additive noise channel. The second one is going to be linear time invariant filter channel. And the third one is going to be linear time variable filter channel. So these are the three types of channels that we're going to consider. Let's look at first the block diagram of the additive noise channel. This is how this channel looks like. You have your signal, so this is the same signal that comes into the channel and the output of the transmitter. This signal is modified with some gain, which for the theoretical purposes, I say gain. In every practical channel, this is going to be some form of attenuation, right? Some loss of energy. And the signal is also corrupted with some noise. And this is what comes at the output of the channel. So the model for the channel is this. It has some sort of attenuation, and it has noise that corrupts the signal. So this is my channel. In this case, R of t is going to be S times A times S of t plus N of t, right? So that's the mathematical expression here that tells me how does the signal, or how does the channel modify my signal. Here S of t, I should say transmitted signal. N of t is going to be noise. This A is going to be channel gain. And this R of t is received. And I purposely spell them out here because I'm going to be using the same notation for other channels, but I'm not going to define them. Okay? Same definition of the whole. Now, this is the simplest of the channels that I can have. What kind of distortion does this channel introduce to the signal? Can we enumerate what happens to the signal that makes R of t different than S of t? First thing is this A, right? So as the signal propagates through this channel, it gets attenuated. So there are two, I guess, the distortions here. First one is attenuation. What type of the distortion is this? Is this additive or non-additive distortion? It's a non-additive distortion because it's a multiplicative distortion. It multiplies your signal. So it's a non-additive. The second type of distortion here is the signal gets corrupted with noise. So this is additive noise. And this is an additive type of distortion, right? Because you have now the signal that is present in your output that was not present in the input, right? Here, when you have a multiplicative, every frequency that you place in the input actually comes at the output. It just might be attenuated, right? But here, in addition to that, you have some components of the output signal that didn't exist in the itself. So what happens here? Let's just so that we're clear when we're looking here. I'm just going to read this section before. Let's say you have this is T, this is T. Now let's say the signal S of T looks somewhat like this. This is what I feed into the communication system. This is what I feed into the channel. So what comes at the output is the signal that is attenuated somewhat. So this is not going to be as large as this here. And also on the top of it, you're going to have this noise that is going to become a signal. So now this is presented to the receiver, and somehow the receiver needs to look at this and say, oh, it was this that has been said, right? So the receiver needs to do a lot of processing to undo even what is done by the simplest possible channel. Now, this is, as I said, the simplest channel. In many cases, it's the best case scenario, right? So when we analyze our communication systems, we're going to actually first try to benchmark their performance in this channel. There's a special version of this channel where this noise has a properties of being Gaussian and white. And if that's the case, then we define something that we call AWGN. So the special version of this channel is, let me just put here, AWGN. So that stands for additive, white, Gaussian noise. And AWGN is a special version of this channel, and that's the one that we almost all the time consider as the first one when we benchmark the performance of a given communication system. We're going to spend the most time working in this channel because we're at the beginning, right? So we're going to try to understand what does this channel do to our signal and how we can send a signal through this type of channel. Okay, so the next type of channel is what we call linear time invariant filter channel. So this is two linear time invariant filter channel. The block diagram for this channel looks like this. You have, again, your input signal here, but then the channel acts as a filter that I'm going to specify through its impulse response here. And also, the signal is corrupted with the norm. So now, these two together make a channel. And this is your output signal. In this case, the output signal R of t is S of t in convolution with h of t plus n of t. Okay. In this expression here, this star, as you probably know, indicates the convolution operator. In its expanded form, R of t can be written as integral when tau goes from minus infinity to plus infinity, S of tau, h of t minus tau, d tau, plus n t. Or, which is the one of the theorems, these two are interchangeable, so I can have tau goes from minus infinity plus infinity, S of t minus tau, h of tau, d tau plus t. Okay, so so this channel, just like the previous one, introduces a set of distortions. Now let's take a look at what are the distortions that are introduced by this particular channel. First thing, so let me kind of enumerate distortion. Amplitude of the signals, amplitude of the signal components have changed. Also, the phase of the signal and then the third one is you still have additive noise. These two are, again, non-additive distortions. This is an additive distortion. Now, these two statements are somewhat ambiguous at this point, because some of you know them from earlier courses. But in this course, we're actually shed a lot of light on what does this mean. What I promise you here is that you're going to stop seeing the signals as their time domain representation most of the time, but you're actually going to see them as a whole bunch of sinusoidals that are lined up in a particular way to form this signal. And what this channel does here It looks all of these individual sinusoidals and treats them in a different way. That's a fundamental difference between this channel and this channel. This channel would treat every sinusoidal the same way. It will attenuate every sinusoidal by the same amount. Here, the channel may prefer certain sinusoidals over the others, and that's that filtering aspect of the channel. They amplify certain portions of the spectrum and attenuate certain other portions of the spectrum. So that's the linear time invariant channel. This is actually more realistic channel. A lot of real channels behave like this. None of the channels behaves like a WGN over the entire frequency range. We can approximate it if the bandwidth of your signal is much smaller than channel bandwidth, but this is kind of just a mathematical fiction. Some of the real channels may actually behave like this. And typical, I'll go through some typical examples in just a second. So any questions on that? Right? So when we in this course, when I say, okay, let's look at the transmission through the linear time invariant channel, what we're actually going to do, we're going to say, here's the channel, it has this impulse response, and it has the noise with this particular characteristics, and then this will fit to this particular channel. The last channel that we're going to talk about is linear time invariant channel. The model for this channel looks like this. This is your input. You still have an impulse response, H, but now it's H of t at some time tau, right? Some time. And I'll explain this a little bit in more detail. And then inevitable noise added to the end to produce your R of t. So now this whole block makes the channel. Now, how is this different than this channel? This one is this channel here is the same regardless of when you look at it. If I transmit through this channel today and tomorrow, the impulse response of this channel will stay the same, right? So that's the time invariant piece of it. Means that the impulse response of the channel does not change over time. There are channels that have impulse response that are also linear filter channels, meaning that they can be modeled like this, but the impulse response changes over time, right? That's the time variability of this channel. Now, how do we calculate R of t in this particular case? The channel is still linear, therefore the convolution still holds. So I can calculate here R of t, but at some time tau is going to be equal integral when u goes from minus infinity to plus infinity s of mu h of t minus mu at a given tau d mu. Okay, so I have to now, mu is just a running dummy variable. It helps me do the integration. Here, what you have embedded is that if I take the same signal, S of t, and I feed it into this channel at two different times, tau, I'm going to get the different output. Right? And that the input-output relationship is still linear, it's still convolution, but the impulse response of the channel changes over time, and therefore, even the same input fed at two different times will give me different output. Okay. Now, this may seem a little bit, at this stage, without any examples, it may seem a little complicated, but you will see that this is not uncommon. As a matter of fact, some of the most common channels that we use exhibit this kind of problem. So let's first look at an example of the linear time invariant channel, and then look at the example of the linear time invariant the time variant. So example 1, this is linear time variant channel. The most common linear time invariant channels have transfer characteristics, which is your age of atom, which you know is Fourier transform of age of t. And so that looks somewhat like this. This is your typical low-pass filtering channel. This fits this mathematical model describes in a pretty good accuracy all of your electrical wire line channels. If you look at twisted pair, it has a transfer characteristics that is somewhat like this. If you look at the coaxial cable, this is linear time variant channel. An example of that is your wireless communication channel. Okay. So how does the channel look in this particular case? Well, here's what you have. You have your transmitter from which you're going to send your signal, and then you're going to have your receiver, or just to make sure that we understand that there's mobility involved here. There's some vehicle here moving around. Let's say this is a radio broadcast. This is my car here receiving the signal. Now the signal gets to this antenna several ways. There's a way that travels directly. Then there's a way that reflects from this building. There's a way that reflects from the ground. There's a way that reflects from far away here and reaches this particular channel. So now think about what happens if I send a pulse, and ideally, theoretically, if I send an impulse, right? Well, there will be a several replica of the signal that I have sent that are reaching my receiver, right? So let's take a look at now this time t. And let's say this is my impulse response at some time tau, and I'm going to let tau axis run like this. So this is, let's say I send a pulse now, and I'm just going to simplify it, assuming that I'm sending the pulse, and I'm going to put what comes at the output. Let's say I get the first reflection, that's my direct wave. Then there is this guy here that comes a little bit after, but it's somewhat attenuated. There's this guy that comes quite a bit after, attenuated even more. And there's this one that comes, here, right? So I have 4 responses to my signal impulse that I have sent over the channel. Now, I let time go by, and then I send another impulse. So what happens in this case? Maybe this one comes here, there's another one, there are 3 more here that are coming, and so on, right? So you can now see that this is here, tau equal 0, tau equal tau 1, tau equal tau 2, and so on. So you can see now that if I send an impulse at different times, I'm going to have a different channel, a different impulse response, right? And because of the mobility of the receiver, the impulse response of the channel changes all the time, right? Even you can see, when we talk about wireless channel, even if this receiver stands still, the environment itself is not still, right? So maybe there's a reflection here that came from another vehicle. Even if this one stands still, the reflection from this guy is going to change over time. So the point here is that in a wireless environment, your channel is changing constantly, and you have to be able to accommodate for that. Now think about how demanding the task is. You're sending a signal into the channel that can change anytime, right? And it does change all the time, right? So now you have to be very smart to adapt your transmission and reception so that no matter what happens to the signal, your receiver has enough knowledge to undo the effects of the channel, right? And that's what happens every time you pick up your cell phone to communicate over this channel. There are other types of channel that we didn't cover here, right? Just let me know them. But all the channels that we have covered are so-called linear channels. Channel is linear, it's described through linear system theory, right? If the superposition holds, convolution holds, you know, I put two signals at the input, I expect to see two signals at the output, they're not mixing together. Majority of the channels, due to the nonlinear devices that you have along the way, so all the power amplifiers, mixers, all of those things, would actually introduce some sort of nonlinearity. And what happens is, you know, the signal now gets additional distortion, which results from that, where there's a mixing in the spectral component. We're not going to talk about it in this course, just be aware. But you can have, again, nonlinear channels that are time invariant, nonlinear channels that are variant, and so on. And usually, you know, when we analyze those, it gets pretty complicated pretty fast because, and to be honest with you, we don't really have good math to describe these channels, and we deal with them on a case-by-case basis. We talk about these channels a lot when we talk about in the course that we have here, that's called wireless design concepts, where we actually talk about properties of the power amplifiers and the distortion that they introduce into the signal. So, any questions about any of this? Okay, so where we're going to go from here is, as I said earlier, this is the only time where we're going to talk about the channels. You know, we're going to, from now on, use appropriate channel model to deal with the transmission. And we're going to focus, transmission and reception, and we're going to focus on two basic blocks, transmitter and receiver. But before we go there, we'll have to assess the properties of the signal and develop some math that will help us understand how do these signals actually propagate through channels? What actually happens? And for that, we need to kind of review some basics in Fourier analysis. So we're a little bit early for this first section. So let's stop and give you guys a break, 15-minute break, and then we'll come back.
Okay.
If you want to sell online, make sure you stand out. Go to Wix e-commerce and create a professional online store that will grab shoppers' attention. Build a state-of-the-art storefront and make it your own. Showcase your products with striking product pages and sell subscriptions. You can practically smell the beans. Go global and display prices in local currencies. Want to boost your sales? Grab a coffee and chat with your customers to offer.
Okay.
You guys hearing me?
Yes, sir.
Okay. I wonder why whenever I, okay. All right. So that's the general overview of the course. So next week we'll start by taking a look at the Fourier transform, and then we move from there. I'm going to assign for you some reading. So on any one of those texts that would have sung the syllabus, you read the introductory chapter, which will be essentially a revision of the video that we just watched. All right, so with that, we're gonna stop here for the day.
All right, sir. Take care.
Okay,
Okay.
sir.
Okay, sir.
Yeah.
Oh, sir, I have a class. Well, no, I was going to say I have a class at 3, so I might not be able to compile and upload the video until the end of the day about.
Okay, that shouldn't be a problem. Okay. All right, take care. Thanks.
Yes, sir.